All right, welcome to season 18. This season is going to be all about really understanding water in our atmosphere. And so we're going to talk about things like humidity and clouds and precipitation. All those kind of things are going to fall into this chapter. Let's jump into this. The first concepts that we want to look at are, first of all, we kind of want to just review a little bit about the water cycle. Not the water cycle, changes of state. That's what I want to talk about, because that's going to be important into understanding our big concept for this first lesson, which is humidity. Humidity is probably one of the most interesting, but can sometimes be complex concept because there's a lot to think about. But we're going to break it down so we can understand this concept well. All right, here we go. To start, water in our atmosphere, right? To understand everything that's happening up in the atmosphere, while we looked at all the different things that can affect temperature, in this unit, we really want to focus on this, water vapor. And what is happening to water vapor in our atmosphere? Because if we can understand this, really we can understand a lot of how weather works, all right? And so we have that. When we start talking about water vapor, we talked about that. This is every form of condensation, including precipitation, which basically we're talking about any water that falls from the sky, from a cloud. But in general, we want to talk about all the water in our atmosphere. And since we want to talk about water, we want to do the simplest review. And the simplest review would be, okay, think about water. Think about the states of matter. What does water look like in the three main states of matter? All right, hopefully you came away with these three concepts, right? We got liquid water, we got solid water, which we call ice, and we have gaseous water, which we call water vapor. Okay? So we have those three forms. But when it comes to this, this picture here, simple diagram, it's probably something you understand really, really well, right? It's something you've gone through so many different times throughout your scientific career as a student. But you have this, right? You know that water can freeze and turn into ice. You know that ice can melt and turn back into liquid water. You know that it can evaporate into a gas. You know it can condense into that. These top and bottom terms are the terms that we often forget about. The fact that it can skip the liquid phase. It can go right from solid to gas and right from gas to solid. That can happen even in water. It's not the most common thing to see. It's a really hard thing to see. Carbon dioxide, if you've ever seen a fog machine, that's what's happening, is solid carbon dioxide is being changed into this. But why does this happen? Right? The easy answer, the simple answer that we often go to is temperature. A change in temperature causes a change in state. And you would be wrong. Maybe not 100% wrong, because, right, your wonderful kindergarten teacher, first and second grade teacher taught you that. It's temperature. As you get hotter and colder, things melt and freeze and whatnot. But the reality is it has more to do with energy. To go from a state to a different state, it's how is the energy moving in that environment? And you might say, well, isn't that temperature a measurement of how that energy is moving? And that's where I'd say, yes, that is very, very true. All right? And so we can look at that, right? We can talk about the amount of energy, right? Here's a number for you. To move from liquid to solid or vice versa, it takes 335 kilojoules of energy per kilogram of that substance, right? Kilojoules of energy. Compared to go from liquid to gas or vice versa, it takes 2,257 kilojoules. So a lot more energy. That's the key idea here, not necessarily memorizing the number, but it takes a lot more energy to go from liquid to gas and from gas to liquid than it does to go from liquid to solid. Almost 7 times more energy. But this is more often what we're seeing in our atmosphere. And there's a lot of energy up there coming from the sun's radiation, right? So we have that. And if I want to skip this middle phase, right, I add these two numbers together and I can skip the phases if I can get enough of that energy for things to happen. And so energy is the key idea. But I told you you were wrong, right? You were wrong about temperature because these changes have everything to do with energy. And here's the reality. It's called latent heat. Latent means hidden. And the reality is, remember, heat, while it can be measured in temperature, heat is the transfer of energy. And because energy is the key idea here, we get these terms. We get the latent heat of fusion and the latent heat of vaporization. Because it's that heat, it's that transfer of energy that causes a change of state to happen. And at that moment in time, when it changes from a solid to a liquid or from a liquid to a gas, there is absolutely no temperature change. There's just transfer of energy. Where does this happen? Most often it happens at those temperatures that you memorize. 0 degrees is the freezing temperature and the melting temperature. But if they're the exact same temperature, this is where latent heat comes into play. Where is the energy going? Because both happen at 0. Just like if I go from liquid to gas and I say 100 degrees Celsius, both processes, evaporation and condensation, happen at that same temperature. And so it has to be the transfer of energy, it has to be the latent heat that causes the change as things go on. Quick little review. Maybe you remember that from physical science. Latent heat. Heat of fusion, heat of vaporization. Right? Key idea here. That's important. We got to have energy, and the energy found in our atmosphere is going to cause changes. What kind of changes are we going to see? Because temperature is going to play a role, but it's not necessarily the key factor. All right, so that gives us these first 2 points as we look at this. All right, let's jump into our next major bullet point. All right, we got these ones. All right, now we want to get into this concept of humidity, and there's a lot to talk about. All right, here we go, humidity. All right, when it comes to humidity, we can break humidity down into a couple different things. One, we want to know just what is humidity, and we've got a simple definition here is how much water vapor is in the air. That's what humidity is. And as simple of a definition as it is, humidity is probably the most complex idea in weather. And I say that because there's so much to think about, all right? But let's break it down and make it understandable, all right? The other problem that makes it so confusing, excuse me, is this concept. When we look at humidity and you listen to a meteorologist talk about it, you're going to hear relative humidity, you're going to hear the word dew point, you're going to hear the word heat index, and for a normal person, you're going to hear those three things and you're going to say, oh, they're talking about something different, right? Different terms, different things, but they all talk about humidity in slightly different ways. And some of them can make it seem a little bit, what's the word I'm looking for? Unclear. It's almost like they're hiding the truth from us. So I'm going to unlock that answer to you. So if you like listening to the weather, you can understand these terms and you understand what it is they're talking about. All right? Quick little video. All right, so we start with humidity, right? There's water vapor in air. How does air do it? How much water vapor can air hold? And that's what this picture is, and this is a picture that maybe is worthwhile thinking about. We know that H2O, water, changes forms. We just talked about that in that first little video talking about solids, liquids, and gases. Right? So they're changing forms. And when we look at this, when we start to understand humidity, we need to understand what's called saturation. And saturation is thinking about the idea of how much can a substance hold, right? If something is fully saturated, it's completely filled with whatever it is you're trying to fill it up with, right? So if we're thinking about water, right? If I want to fully saturate something, I'm filling it to its maximum. It's going to be completely saturated. But humidity is going to be a measure of how saturated something is. So this is what we can see, right? Assuming we have a cup, right? It's sealed, it's got a cover on it. Our water is at room temperature, right? And as we look at this, right, eventually room temperature, right? If we get enough energy, we're going to get evaporation starting to take place, right? So if we pump some energy into here, right? If there's no water molecules in this air here, just for sake, right? 0, we're going to have 0 saturation, right? If we put 10 grams per kilogram, right? Now our percentage has gone up. And because our percentage has gone up, we have more saturation, right? It's getting filled with water vapor. And if we continue to add water vapor into this section, right, it's going to continue to grow until it can no longer hold any more water vapor, right? And if you get to that, it is considered fully saturated. And RH stands for relative humidity. The relative humidity then is 100%, which means it's completely saturated, completely full. And when we talk about RH, or relative humidity, that's often what we're talking about, is how full is the air, right? And so we can look at this, right? And we can actually do some math if we really wanted to, right? And understand this. When we start talking about air being saturated, there has to be a balance between the liquid water changing into that vapor or that gas. So that's one change that we're considering. And we have to think about the vapor changing back into the liquid water, right? Remember, it can go both directions when changing states. So there has to be a balance of what's going on. Once we get fully saturated, this is the phrase, right? The air can't hold any more water. How can you measure these things? You can start looking at different things. You can look at the temperature of the air and compare it to how much water can be held within that air. And then you can do a calculation, right? And so here's my example here, right? If I have -4 degrees Fahrenheit, that means I can hold 0.075 grams of water per kilogram of air. Which those numbers are a little bit hard to understand, right? We don't fathom those things, okay? 0.7, we get this kind of picture, all right? 1 gram, that's like a paper clip. A kilogram is like an apple, right? So at 4 degrees Celsius, it's like there's about a paper clip's worth of an apple of water vapor. I don't know if that helps you at all. All right, that's the best picture I can come up with the top of my head, right? Not that much water, but could have a very different feeling, right? Compared to if I come down here, right? If I get much, much warmer, right? Now I'm at 68 degrees. Now I can put 14 paper clips, same apple. It's gonna feel very different. Try taking a bite out of that apple. Higher chance of getting a paper clip in your mouth. I don't know why you would eat an apple with paper clips in it, but if you do, just be warned. Higher number of paper clips, higher chance of biting into a paper clip, right? But that's the concept, right? Big idea here is this. If I have warm air, I can hold more water. It can saturate more. can put more water in hot air than I can in cold air. Key idea. More water vapor than cold air. And this is where it gets fun, right? This is where it gets fun. Because now we get this, excuse me, we get this term, relative humidity. Relative humidity is just that, it's relative. Relative to one, what kind of air, warm air, cold air. So the temperature of the air, and how much water then is inside of it. So we look at the ratio, the comparison of how much water is there compared to how much water it could hold. Right? So this is how much water is there, this is how much water could be there. And we make that comparison and we change that into a percentage. And as we look at that, we call that relative humidity. And what that tells us is not so much how much water is in it, that's what it gets confusing, but it just tells us how close to saturation are we? How close are we to being full, not how much water is actually in it. Right? It's like pouring yourself a glass and you can now look at this glass and say, yep, that glass is half full. But I can fill up a 5-gallon bucket and fill it halfway, and I can also say that one's half full. And according to this principle, relative humidity, they would both be at 50% because they're both half full or half saturated. But no way would you say they're the same, because that 5-gallon bucket is huge. That's way more, I mean, it's got cups and cups and cups of water compared to your single cup. Relative humidity. It's a little misleading. It's a little confusing. That's why we have absolute humidity. Absolute humidity tells us the quantity of water. The problem is meteorologists don't like to talk about this. They like to talk about relative humidity, or they like to talk about dew point, or they like to talk about heat index, or what it feels like. Maybe that's a phrase you've heard, right? So we have this idea, right? Relative tells us how close to saturation, not the quantity. Not the quantity. I need a drink. All right. Here's the big idea here. All right. As we look at this, these are really awesome charts. They give us awesome information about things. If I didn't print this out, tell me to print this out. All right. This is hard to read. I'm going to give you a better picture of this. Okay. And you can throw it in your notes then. But this is the big picture as we look at humidity, right? Maybe in your notes or the sheet of paper I gave you, you write, this is talking about absolute humidity, like it does over here. I don't, right? So humidity or absolute humidity, this is often when you just hear the phrase humidity, that's what scientists are talking about. It's just that, right? The amount of water in the air compared to relative humidity is just the percent of how much could be in the air, right? Here we have a measurement, here we have a percentage. Now my ruler, all right, here we go. Here we have the concept of how much water is actually there compared to how much could be there, right? Or how much water vapor is there divided by the volume of the air that is actually there, right? Where this is the pressure of the water vapor, equilibrium of the water vapor divided by the given temperature. So it's completely based, relative humidity is completely based on temperature. How much could be there, right? That's the idea, relative, it could be there, isn't necessary, right? Why is this important, right? You need to know absolute humidity when it comes to boiling an egg or working with these things, because that's going to make a major difference. Compared to relative humidity, that's where your air conditioner, HVAC systems are going to use those kind of numbers. steam turbines are going to use those kind of numbers. They're going to use relative humidity to see how much more those machines can put out. All right. So we have those ideas. All right. This is a great one. Right. Absolute humidity is totally independent of the temperature. Independent of temperature, while relative humidity, if temperature goes down, your capacity goes down. If temperature goes up, your capacity goes up. And so these numbers can be very different, right? Small cup, big bucket. Relative humidity, dependent on temperature. So we see these things. Whew. Humidity, it's huge. All right, let's end up this section looking at, right? So our humidity, I gave it to you, I described it for you. Bring your questions if you still have them, right? As you look at this. Factors, okay? Well, what's gonna change this kind of stuff? What do we need to keep in mind as we think about humidity, whether it's absolute humidity, relative humidity? We're gonna talk about dew point and heat index in this last section as well. To change relative humidity, right? Keyword relative, the possibility. To change relative humidity, we need to add or remove water vapor. First thing. Second thing we're gonna do is we're gonna change the temperature, right? Absolute humidity is really just about this. Relative humidity is about both of these things, right? Because absolute humidity has nothing to do with temperature. Relative humidity does. It's all about temperature. All right, so we have this concept. As we look at this then, we can see some kind of interesting things, right? Even just this idea, right? We got temperature, which affects relative humidity, right? But doesn't affect this. Look how the colors change. Look at the colors just between this one and this one, right? This is saying, right? The red says 100% humidity up in this freezing area. But why? Because the temperatures are so low. It doesn't have a lot of water in it, but it can't hold a lot of water, so it looks like it's very full compared to down here in these regions. Where am I trying to go? This region, right? The Sahara Desert. There's not a lot of water there. It's a desert, right? But it's also very hot there. It could have just as much water as here, right? Look, blue here, just as much water. It's just the capacity is so much higher, right? Which is what this is talking about, right? Lowering air temperature will lower the relative humidity. Lower. Raising the air temperature will raise. Did I say that right? I didn't say that right. I'm saying that wrong. Let's try this again. When water vapor, so what am I talking about here with these pictures? Let's start over one more time. So what am I talking about here with these pictures? Right? It's this concept here. When water vapor content of air is constant, right? So the amount of water hasn't changed. If I lower the air temperature, I'm going to increase my relative humidity. If I raise my air temperature, I'm going to decrease my relative humidity. Water amount stays the same. Percentages are going to shift based upon the temperature of the air. Relative humidity. It's cool. It's a neat concept. It's a little misleading. So now we get into words like this, dew point. This is our explanation to dew point, right? The temperature that a parcel of air would have to reach to reach saturation. Wording, right? Science wording, right? So basically what it's saying is, if I want to make it to the dew point, is if I have this amount of water, right? I have a given amount, let's say 5, just for a number, right? What temperature do I have to be at so that 5 is full, right? It's the full cup. That's what dew point is. And that's what we're trying to figure out. Where will the air be fully saturated with water vapor? Dew point, right? What temperature do I have to get to be full, to be fully saturated, right? And here's the general idea. Every 10 degrees Celsius, the amount of water needed is doubled. So let's say at 5, I have 5 grams of water. At 10, let's say it's full. If I go up to 20 degrees Celsius, that 5 is now only half. And I would have to double this amount. If I go up another 10 degrees, I'd have to double it again. So now I'm only at like a 20%. Double, 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 right? The math is there. We'll work through some of this math so we understand it and see how the numbers work when we're dealing with dew point and relative humidity and understanding these values. All right. So, relative humidity. It's a term that's used less and less in meteorological reports, news reports about the weather, right? And here we see this more often, low dew point versus high dew point. So what does that mean, right? A low dew point means that our sweat is going to evaporate easily because there is room in the air for more water molecules. Typically means, right? Why would there be more room? The temperatures are warmer, right? Temperatures are warmer, right? But this can happen during the summer too. You can have warm air, but just have a low dew point. There's just not a lot of moisture in there. Compared to a high dew point, right? Sweat builds up and won't evaporate because there's nowhere for that sweat to evaporate to. It doesn't need to go into the atmosphere, right? Because the air is already full of water. High dew point. You're gonna sweat. You're gonna sweat. Thought I had a slide on heat index. Let's jump to here because I don't want to miss it. Heat index. Heat index is a term that has to do with what does it feel like, right? So very often what we'll do is we'll take relative humidity, so the possibility of humidity, compare it to the temperature, and then we'll match those up, right? So if we said it's 70% relative humidity and it's 88 degrees, what's it gonna feel like? When you go outside, it's gonna feel like 100 degrees outside, right? Because of the moisture in the air, even though the air temperature is only gonna read 88. Right? And that's what heat index is all about. One of our activities is gonna have us working with this table. I'll give you a copy of this table. You don't have to copy it all down. But just understand that that's what heat index, write that in. Heat index feels like. What does it feel like? What does the air temperature feel like? Because of the moisture in the air. All right. All right, those are just more tables. We'll work with those. Last idea in connection to humidity. Where do we come up with these numbers? This is where hygrometers come into play. A hygrometer is a machine that measures humidity. Now, when it comes to hygrometers, there's different kinds of hygrometers. The kind that we're going to use in class is called a psychrometer, right? And they can look like this. This is what we're going to use. And they can look like this as we look at that. This is electronic, has all this stuff in there. It finds the readings for you, but that's not fun. So we're going to use the old-fashioned way, all right? Well, the old-fashioned way was you looked at a girl who had curly hair, and if her hair was curly, you said, oh, it's humid today, right? Or if their hair is normally straight and it's curly, you'd say, yeah, it's curly day because that's an effective humidity on hair, right? More scientific way than that, though that was the science for a while, crazy. More scientific way is we're gonna use thermometers and we're gonna have dry bulbs and wet bulbs. And so basically you have something that's dry and then you put this towel over another one and make it wet or damp, and then you spin them in the air and your thermometers change. And as your thermometers change, you can now compare the two numbers that you get to all these different tables, and you can look at all these different tables and you can come up with the numbers, all right? And in the end, what you're looking for, right? Remember, temperature is the change in energy. The psychrometer is going to show you that change in energy. All right. Whew. It's a lot. It's a lot, but it's good stuff. We're going to spend some time looking at humidity.